When two asteroids collide in space, the outcome can vary depending on various factors such as the size, speed, composition, and angle of impact of the asteroids involved. Asteroid collisions are dynamic events with complex outcomes that depend on various factors. Let's explore the potential scenarios. 1. High-speed impact. If the asteroids are traveling at high speeds relative to each other, the collision will generate an immense amount of kinetic energy. This energy can cause fragmentation, shattering the asteroids into numerous smaller pieces. The impact can be so forceful that it might vaporize some parts of the asteroids, creating a plume of debris and ejecting material into space. The collision may also generate shock waves that propagate through the asteroids, further breaking them apart. 2. Low-speed impact. In a low-speed collision, the outcome might be different. Instead of fragmentation, the asteroids may merge or stick together due to gravitational forces. This could result in the formation of a larger asteroid or a rubble pile, depending on the relative sizes and compositions of the original bodies. If the asteroids are loosely bound collections of rocks and dust, rubble piles, they might break apart upon impact, scattering debris in various directions. 3. Angular impact. The angle at which the asteroids collide can significantly influence the outcome. A head-on collision might result in a more violent disruption compared to a glancing blow. A direct head-on collision could lead to the destruction of both asteroids or the formation of a new, possibly irregularly shaped body from the remnants. A grazing impact might cause one asteroid to deflect off the other, altering its trajectory while leaving both bodies relatively intact. 4. Secondary effects. The collision may generate heat due to friction and compression, potentially melting some of the asteroid material. Depending on the composition of the asteroids, the impact could release volatile substances trapped within, such as water, carbon dioxide, or methane, altering the chemical makeup of the debris cloud. The collision debris may spread out in a cloud around the impact site, forming a temporary asteroid belt in the vicinity. 5. Long-term effects. The collision aftermath may include a cloud of debris surrounding the impact site, which could pose a hazard to spacecraft passing through the area. Over time, gravity will act on the debris field, causing it to coalesce into smaller asteroids or dust particles that may eventually settle onto other celestial bodies or continue orbiting as smaller asteroids. Factors affecting the outcome, size and composition. A larger, denser asteroid will have a more significant impact on the collision outcome. Asteroids made of looser materials, like rubble piles, are more likely to shatter upon impact compared to those composed of stronger materials like iron. Its impact velocity, which means higher speeds, translate to a more violent collision, with a greater chance of shattering and widespread debris. When two asteroids collide, the outcome is determined by several factors, including the size, speed, composition, and angle of the impact. Here's a breakdown of the reasons behind what happens during such collisions.
1. Kinetic energy. Asteroids in space move at incredibly high velocities. When two asteroids collide, their kinetic energies combine, resulting in a tremendous release of energy. This energy is responsible for the fragmentation, melting, and vaporization of asteroid material. 2. Formation of satellite bodies. In some cases, asteroid collisions can lead to the formation of satellite bodies orbiting the larger remnants. These satellite bodies may consist of fragments ejected during the collision or material accreted from the debris cloud. The presence of satellite bodies provides insights into the dynamics of the collision and subsequent gravitational interactions.
2. Low-speed impact. In a low-speed collision, instead of fragmentation, the asteroids may merge or stick together due to gravitational forces. This could result in the formation of a larger asteroid or a rubble pile, depending on the relative sizes and compositions of the original bodies. If the asteroids are loosely bound collections of rocks and dust, rubble piles, they might break apart upon impact, scattering debris in various directions.
4. Heat and pressure. The collision generates extreme heat and pressure at the point of impact. This can cause the asteroid material to melt, vaporize, or undergo chemical changes. The release of heat and pressure can also contribute to the fragmentation and alteration of the asteroid's composition. 5. Ejection of debris. In addition to the fragmentation of the colliding asteroids, the collision can eject debris at high velocities into space. These ejected fragments can travel significant distances from the impact site and may pose a hazard to spacecraft or other celestial bodies in the vicinity. Some of this debris may enter orbit around larger bodies or contribute to the formation of asteroid families and clusters. 6. Crater formation. If the collision occurs with sufficient force, it can create impact craters on the surfaces of the asteroids involved. These craters result from the excavation and displacement of material during the collision. The size and morphology of the craters provide valuable information about the energy and dynamics of the impact event. 7. Shock waves. Collisions produce shock waves that propagate through the asteroids, further disrupting their structure and accelerating the fragmentation process. These shock waves can also eject material into space, creating plumes of debris that spread out from the impact site. The intense pressure and shock waves generated by the collision can induce shock metamorphism in the asteroid material. This process involves the transformation of minerals and rocks due to the extreme conditions experienced during the impact. Shock metamorphism can produce unique mineralogical signatures that help scientists study past collision events and their effects. 8. Angular momentum. The angle at which the asteroids collide plays a crucial role in determining the outcome. A head-on collision results in a more direct transfer of kinetic energy, potentially leading to more violent fragmentation. In contrast, a grazing impact may cause one asteroid to deflect off the other, altering their trajectories while leaving both bodies relatively intact. 9. Regolith redistribution. The collision can disrupt the regolith, surface layer of loose debris, on the asteroids, redistributing it across the surface or ejecting it into space. This redistribution can alter the surface properties and appearance of the asteroids, affecting their thermal characteristics, reflectivity, and erosion patterns. 10. Gravitational focusing. Over time, gravity acts on the debris field generated by the collision, causing it to coalesce into smaller asteroids or dust particles. These smaller bodies may continue orbiting as remnants of the original collision or settle onto other celestial bodies within the vicinity. The larger fragments, especially from metallic asteroids, might have enough mass to exert their own gravitational pull. Smaller debris within the collision zone could experience a tug-of-war between the gravitational pulls of the larger fragments.